So the idea now is that once we have designed the heat exchanger network, it would be nice to just verify that the design cannot be improved. And so what does it mean? It means that we have to be sure that there is no way to reduce the number of heat exchangers, and perhaps that the question, the remark of having a very small heat exchangers is perhaps not the best idea, and removing one heat exchanger could perhaps save a lot of money in investment without penalizing too much in the operating costs. Okay, so the idea would be then to see if we are able to alter or change the design in such a way that we will reduce the total costs. Okay, and for this I would then have to introduce a new notion of the delta T minimum, which is the delta T minimum allocated to one heat exchanger. That is what we name the EMAT, exchanger minimum approach temperature. So how can we do this? So let's assume that I have this design, which was the design that I have just made, and from which I have verified that I have a given investment and at the end an operating cost as well. So I can then sum up the two to have the total cost of the system. And what I have also seen is that looking here at the number of heat exchangers, what I can see is that I have 1, 2, 3, 4, 5, 6, and 7 heat exchangers. And when I'm applying the minimum number of units rule that I have calculated, which is telling me that the minimum number of heat exchangers is the total number of streams minus 1, so 6 minus 1 makes 5, plus the number of heat exchangers of streams crossing the pinch, so 1, 2, 3, minus 1. So normally I should have found 5 plus 2 heat exchangers, and if I'm making the total, I have exactly 7 heat exchangers, which allows me to say that, okay, I have at least a reference solution which has 7 heat exchangers, and that has a total cost of 22 Swiss francs per year. Now, if I want to try to reduce the number of heat exchangers in the system, in fact, there are 2 tricks. The first one is what we name the path following. The path following is identifying in the heat exchanger a path from the hot utility to the cold utility. Okay? For example, I can find a path that is linking the hot utility here with the cold utility here. And I'm passing through the E3. Okay? So it means that if I want to suppress the E3, which is here, what I can do is to add 120 kilowatt here, and therefore this one will not be needed. And I will add 100 kilowatt here, and I will have 65 plus 120 kilowatt in the cold utility. Okay, so this is a path that is identified, and the path is going to allow me to do to realize a calculation along the path. So it means that if I'm adding a certain amount of heat in one heat exchanger, the consequence is that the next one will be reduced by the same amount, and then the third one in the path will increase by the same amount. So I have effectively the same energy balance at the end, more in the hot utility and more in the cold utility. But the advantage is that if I'm adding 120 here, I will need 120 less here. And as this was the size of the heat exchanger, it means that the new design will have one heat exchanger less. Okay? But the price to pay, in order not to buy this heat exchanger, is to pay for the hot and the cold utility an increase in the total amount. So now I can obviously recalculate all the heat exchangers except the E3 that has disappeared. So each one of the temperature is going to change in the system because I have removed the heat exchangers. It means that the temperatures that will be seen here and here can change, the same here. And at the end, I will have a new investment for the system, and I will be able to add a new line in my list saying that, okay, I have one less heat exchanger, but the investment has been reduced. You can see that there is a big change in the investment, but the operating cost has been increased a lot, which means that the total cost is higher in this case. Okay, but there were other paths that could be identified. So for example, going from here via the E2 through the E5 to go to the cold utility. So if now I'm doing this path, so what I will identify is that now if I'm adding, so I'm identifying the smallest one here, so the E5 is the smallest one. So if I'm adding 15 kilowatt here, the E2 will be minus 15. Going back via the E4 means that the E4 will have to be increased by 15, but if the E4 is increased by 15, then the E5 will be reduced by 15, which means that the cooling requirements will need to be increased by 15 if I want to satisfy the needs of all the streams in the path, right? So by doing this, I'm going to suppress the E5. So now, again, I have 6 units instead of 7, okay? But this time, the investment reduction is a little bit less, okay? But the penalty is much lower, which means that when I'm going to add this in the list, I will see that I can have something which is cheaper in total cost than the original solution because it has a lower number of heat exchangers, and because I have removed the small one that you were talking about. Okay? So, and this is coming from the fact that smaller heat exchangers could cost a lot per unit of square meter installed. Okay, so it means that now I have to take a decision because the total cost of this one is indeed smaller. There is a second technique that can be used in order to identify which one to remove the heat exchangers, and this technique is what we name the loop in the network. So an example of this loop is the fact that the stream A and stream C exchange twice via the exchanger E1 and in addition via the exchanger E4. Of course, in this case, it is across the pinch. But nevertheless, what I can say is that if I'm increasing the heat load of E1 of 90 kilowatt, I will reduce the heat load of E4 by the same amount just to satisfy the energy balance on the streams A and C. Okay? So it means that it allows me to suppress E4 in this way. Okay? Something which is important here is that I have to verify that the temperature still remains compatible. Okay? But then if I'm doing this, then I will see that I will have a new design with a new heat investment, and in this case with less heat exchangers, because I have then suppressed, starting from this solution, I have to suppress a new heat exchanger, so I have 5 heat exchangers. Now what I can see is that the total cost of this new solution is higher than this one. So the number 4 here is still the best one. But there were other solutions. So for example, another loop can be identified. So in this loop, again, what I can do is to use this loop. I'm starting again from the original design. I can use this loop then to suppress the E5 heat exchanger. So by taking minus 15 there, plus 15 there, then minus on the E2, to finally come back with a plus on the E3. So what is important is that I have always to do plus minus, and I'm not perturbating the hot utility. I'm just changing the repartition between the heat exchangers that are in the loop. Okay, and therefore I can, by this way, suppress the E5. And of course, I have to recalculate all the heat exchangers, meaning that I have to recalculate all the temperatures. And I have to be sure that the temperature difference are still compatible, because I do not have changed the hot and cold utility balance. So I've just changed the repartition. And what you can see here is that after doing all the calculations, I realized that for the E3, because I had to add a certain amount of heat load to E3, the temperature difference between this stream and this one is smaller than the delta T minimum. But it is still feasible, so I can still buy the heat exchanger. Okay? So it means that now I'm going to evaluate, and the heat exchanger that is E3 will have most probably a big will have most probably a big area, because it has a very small delta T minimum, or delta T. And this is then shown here because it is the one that has the highest cost in the system. But in this case, I can still add this in the list. So now I have a new solution with a number of heat exchanger that is 6, and with the minimum energy requirement that I was expecting, but with an investment that is higher than the original design. And the total is, at the end, more expensive than the original design. Okay? So it means that I have played a little bit with the loops and the paths in order to try to see if there were new solutions. And there is also another trick that I can use in order to change the value here, is by saying, okay, but now I can always use the path here to add some heat here, which would allow me to reach again acceptable delta T minimum. So I could then add 15 here to have minus 15 here, which would allow to have, and of course the path will force me to have 15 kilowatt more in the cold utility. But in this case, what you can see is that the temperature difference between this in the heat exchanger E3 will be re-established towards the delta T minimum of the original condition. So it means that what you can see here is that you can play with either spending a little bit more of operating cost in order to reduce the investment that is related to the heat exchangers. Okay, and at the end, if I'm recalculating all the flows in the system, then I will have a new design with a new investment that will then be added in the system here. So for example, this is the line that I have just added now, where I have replaced one heat exchanger. So compared to this one, I have one less heat exchanger. I'm accepting a certain penalty here, and I have an investment that is a total cost that is lower than the original, but higher than the best solution that I have so far. And of course, I could have played with other subsystems. So for example, this one could also be used. And again, I would have to re-establish the temperature difference. So something which is perhaps important here is that you can see that this heat exchanger is not impossible, but for reaching this feasible heat exchanger here and here, I had to play with the flows. So it means that in addition to play with heat loads to try to reshuffle the heat load repartition, I can also play with the flows in order to try to reduce the penalty of the temperature differences. Okay? So this one is not impossible, but has smaller delta T minimum than the one that was expected. But nevertheless, it allows me to calculate a new solution with a new, so this is the solution number 1, with a new design of the heat exchanger with 6 heat exchangers. So now we have, in fact, 7 different solutions, one with 7, 5, 5 with 6 heat exchangers and one with 5 heat exchangers that I can compare in order to identify which is the best one. And of course, the best one is the one that has the lowest total cost, which is the solution number 4, which is going to spend more than the minimum energy requirement that was expected, but that is eliminating a small heat exchanger that is costing too much. Okay? So the consequence is that in reality, when we have to do the heat exchanger network design, we have to, at the end, optimize the design. It means that I'm starting with a configuration and I have ways to improve the configuration. I have the possibility of accepting smaller delta T minimum in some of the heat exchangers if they allow to eliminate small heat exchangers. Okay? To finally reach an optimal value of the heat exchanger minimum approach temperature, which is then specific to the heat exchangers that I have in my design. So officially now I have to optimize the size of all the heat exchangers. So I should normally calculate now what is the best value of each of the temperature differences in each of the heat exchangers in such a way that the total cost will be minimum. So, and this is an optimization problem. I'm not going to explain how to solve it because it's quite complex. We have heat exchangers, and the formula of heat exchangers is difficult. So it depends on the heat load. The heat load defines temperatures. Temperatures are here with a ln to be calculated. So it's not an easy optimization problem to solve. And I have a lot of degrees of freedom because at the end I have to decide what is the best delta T of each of the heat exchangers in my system in such a way that the total cost of the whole system is minimized. So it means that I have to calculate what is the best area of each of the heat exchanger. Knowing this area, I will be able to calculate the flow in the hot and cold utilities. Knowing the cost of each of the hot utilities and the time of operation, I will be able to identify what is, at the end, the best configuration. Solving this kind of problem is quite complicated, and most of the time the people stop just before. Okay? Just because it is not so easy to find the optimum. Knowing that in most of the cases we will deal with a big number of streams, which means a lot of heat exchangers, and each one has to be optimized. And as soon as I have a split, I have to calculate what is the split factor as well, which is even more complicated. So the problem is known as being a nonlinear programming problem, which is quite hard to solve. Which means that, as a conclusion, we can say that we have seen that we have a sequential method that allows, provided that we have selected the right value of the delta T minimum that allows to make the heat exchanger network design. Systematic methods that allows to see if we can or not remove heat exchangers by applying either the loop identification or the path identifications, which allows us to have a first guess of what are the most attractive solutions to be compared, knowing that if we want to be really rigorous, we have afterwards to apply optimization methods to define what is the best size of each of the heat exchangers inside the system that we have designed. Okay? The big difficulty of this approach is that it is sequential. So it means that if you decide to start from the biggest MCP with the biggest MCP, and your neighbor decide to start with the two next one, most probably you will end up with a different heat exchanger network design. Okay, which means that afterwards you will have to find new ways to decide what is the best. Just to let you know, when I did my PhD thesis, I was working on this kind of problems, and I have been, for example, demonstrating that it was possible to design for a very simple problem, so 5 streams, so 3 hot streams and 2 cold streams. It was possible to design 7 heat exchanger network configurations, which were completely different, but they were leading to exactly the same total cost. So, which means that without having other ways of deciding, okay, it was strictly impossible to decide. Okay, and it was after optimization, so I did the whole job up to the last digits, okay, and the results were exactly the same, okay, which then means that you will have to be pragmatic, okay, because the things that I have not shown here is, for example, the distance, okay. It's possible that to connect one heat exchanger with another one, there will be 100 meters of pipes, and for another one it will be 200 meters. Okay, and this is not written in my formula here, right? Sometimes it's also dangerous to connect streams. So, for example, never preheat methane with a flow of pure oxygen. Okay, the risk of explosion is quite high. Okay, and there are a lot of those streams that can create also chemical reactions that would then be explosive, or that can create toxic compounds. So same, don't preheat the beer with oil. Okay, because I'm not sure that you will be happy to drink beer with some oil in it. Okay, so but those are pragmatic decisions that you will have to take. Meaning that the method that I have shown is especially a method that gives you guidelines and hints towards the investment to be done in order to do the heat recovery. Okay? Do you have questions? A priori, you should not have questions, because all those things that I have explained, if you never apply it, you will never understand it. Okay? So, which means that you can then, when you do the exercise, try to see what is happening if I'm following a path and I'm calculating, reducing the number of heat exchangers, for example. Apply it, and then you will see what it means. Okay, it's a very good intellectual exercise that trains you thinking systems, and which is something which is very important for all of you. Looking at interactions, I'm adding a little bit of heat there, and all the temperatures are going to change, and this heat exchanger is going to disappear. Those are things that you have to be aware and trained to analyze. Okay? Right, so Francesca is now going to present, so we have 15 minutes to prepare do the next step, which is the presentation of the project. So Francesca is going to make a short overview of what the project, or in fact it's not a project, it's a case study, because we know more or less the solution that you will have to find, okay, that we will use in order to really apply all the things that we are learning together. Okay?